Hello and welcome to this video recording to illustrate this case study in life sciences. This is our studio. This case study involves statistical analysis using R, and the work that I have done is using RStudio. So first of all, I'll show you where I got the data from. This study is about finding the correlation between variables such as physical inactivity, obesity, consumption of fruits and vegetables, etc., with diabetes. And so that's what we'll be looking at shortly. The data that I have used for this has been downloaded from the CDC website. So this is one of the links for getting the data. And there's 3 files that we need to get from here. One is the diagnosed diabetes prevalence. We take the all states. And then the next is the obesity prevalence. We again take the all states file here. And then we have the leisure time physical inactivity, and we again take the all states file here, and I'll show you what these files look like shortly. So this is the leisure time physical inactivity file. It has the state name, the county FIPS codes, the county name, and then data for each year starting from 2004 till 2012. And the same for the obesity file here. It has data in the same format, the codes, the county names, the numbers from 2004 to 2012, and then it's the same for the diabetes prevalence file. And what I have done is I took the percentage numbers for each of these years, so for 2004 and then 2005 and so on, from each of these files to produce a final CSV, and I removed all the records that had missing values or missing data for any of these variables. So what this file looks like now, it has the state, the FIPS code, the county, and then each of these columns, which is the percent, 2004 OB means obesity, and so on till 2012. And then you have the next set of columns for percent, 2004 diabetes, and so on till 2012. And then next you have the physical inactivity percent numbers, again from 2004 to 2012, and this is a consistent naming format that I have followed here. So this is our final input file for some of the analysis that we're going to do. Before I move on, I'll show you what the other data is. So the data for the second set of analysis is from, again, the CDC website. This is the link, annual2013.html. And this is the 2013 annual survey data. And this is the file that we want. Scrolling down to data files, the 2013 BRFSS data. This is the SAS transport format. It's in XBT. It's a .xbt file. And when you download this is a zip format, and then you extract it. And the file that you will get is llcp2013.xbt, and that's what we'll use for our second set of analysis. Okay, so we're back to RStudio, and now what we want to do is we want to load the R script. So I'm going to load it from here. So this is the R script that I have created for the 2 functions in which I have grouped both the analysis. So this is a function plot DM graphs, and then there's another function plot BMI graphs. So plot DM graphs is the part of the analysis that shows the correlation between diabetes, obesity, and physical inactivity from the first input file that we saw earlier. And the plot BMI graphs is the function that shows us the correlation between BMI, which is an indicator of obesity, consumption of fruits and vegetables, which is coming from the second input file that we saw earlier. So once I load this R script here, we want to make sure that both our data files are in the current working directory. I already have them here, but if you want to see what the current working directory is, you can type this into the R console, and whatever folder that you see as a result of this command, that is where you want both of your input data files to be. Also, we need to load the package foreign into our current session. The package foreign is required to import the XPT data file that we saw earlier. So we're going to do that by and so now we've loaded our package. Now we want to make sure that we have the functions loaded here. So but before I do that, I want to execute all these step by step and show how this proceeds towards the analysis. So I'm going to execute the individual steps of the plot_dmgraphs function first. So here we are reading the file county data. So we do that. I'm not going to execute the print functions because that's really just for clarifying when the function executes, but just the data analysis steps. So so next we are extracting the 2012 data for running our graphs. Now we are extracting the 2012 obesity data. Earlier we extracted the diabetes data, and now we are extracting the physical inactivity data. As you can see, all of our variables are getting loaded into the environment here. And now we plot our first graph. This is the diabetes versus obesity graph that we're going to plot right here. So you see this is a positive correlation here between diabetes, percentage population diabetic and percentage population obese, which means counties that have a higher percentage of obese population also have a higher percentage of diabetic population. And the counties that see a lower percentage of obese population also see a lower percentage of diabetic population. Now we'll do the same type of analysis for obesity and physical inactivity. Again, we see this is a positive correlation between obesity and physical inactivity. And now we run the graph for diabetes versus physical inactivity, and again we see a positive correlation here. Now what we want to do is we want to see the trends, how diabetes and obesity have been trending between 2004 and 2012, for which we have the data. So I'm going to place all my year values in this variable years, and then I initiate my vector. What I'm going to do is I'm going to take the average of all the percentages across all US counties so that I have one number for a certain year. So I do that. So now in my AVGI vector I have the average percentage population that was diabetic in 2004 to 2012. I have the average percentage US population that was obese from 2004 to 2012, and the average US population percentage that was physically inactive from 2004 to 2012. And so I'm going to plot that trend analysis here. So this is the obesity line, and one second, this is the diabetes line, and this is the physical inactivity line. And I'm just going to provide a quick legend here. As you can see, I'm simply copying and executing all the steps from my function, and later I will also show what it's like to just run the function and have all these graphs created all at the same time. So this is our trend analysis, and we can see how from 2004 to 2012 the percentage of diabetic population and the percentage of obese population have been increasing steadily. For physical inactivity as well, we see a minor dip here, but overall it's a rising phenomenon. So this is our first analysis that we have done using CDC data showing positive correlation between diabetes and obesity, diabetes and physical inactivity, and obesity and physical inactivity. And so this provides statistical analysis and very clear insights into some of these lifestyle choices that people can make to benefit their health. And now we'll execute all the steps from our second function, which is the plot BMI graphs, and see the analysis that's done between BMI, which is an indicator of obesity, and the consumption of fruits and vegetables. So the first thing we have to do is we have to read our input file, which is the llcp2013.xpt that we got from the CDC website. And so now we create a vector of the specific fields that we need from this file, which is the sequence number, the height, the weight, and the consumption of the fruit juice, fruits, green, orange, and other vegetables on a per day basis. And so now here we have we've selected the specific fields, data for just the specific fields that we want, and now we're going to get rid of any rows that have blank values. So this gets rid of the blank values here. As you can see in this environment section, initially we started with 491773 records, but now after getting rid of the blank values, the records with blank values, we have 421241 records here. And now what we're going to do is we're going to compute some fields. We're going to divide all the fields by 100, because right now it's just an implied decimal value and the fields look a little bit unintuitive, so we're going to just divide them by 100 so they're a little easier to understand. So we do that, and then we also compute some additional fields such as BMI. So this is calculating BMI and adding it to the data frame. This is calculating the total fruits consumed. This is calculating the total vegetables consumed. And this is the total of all fruits and vegetables, the servings consumed on an average on a single day by an individual. Now what we do is we get rid of some of the values that are excessive and so may not be accurate. And per the CDC website, that's if the total vegetable intake per day value is less than 23 and the fruit intake is less than 16, then it's admissible, otherwise we ignore those. So just getting rid of those values. And now what we will do is we'll plot the correlation between fruits and vegetables and BMI here, and this can take a little longer. So this is our graph. This sort of shows a negative correlation. But let's also create the actual regression model. This is the line that gets generated, and it doesn't look like a good fit for a negative linear regression model. So we'll take another variable, which is just the total number of vegetables consumed, and plot that against BMI and see how that goes. So now we're plotting the graph for BMI versus the total vegetables consumed, and then we'll create the model and plot the line here. And again we see, while it's slightly better than the earlier illustration we saw, this is still really, it doesn't clearly look like a negative correlation here. So we will run consumption of green vegetables plotted against BMI gives us a clearer picture. Plot the green vegetables against BMI, create the graph. Now we generate the model and plot the line. We can see this is all negatively correlated with BMI, and this looks like a much clearer picture of a negative correlation between green vegetables and BMI, and again gives us a pretty good insight on how consumption of green vegetables in a daily life can have an inverse correlation with our BMI and essentially obesity, and hence, if you go a step further, perhaps diabetes. All the analysis steps are grouped into these two functions, and now we'll see how to execute these functions. So what we want to do is we want to load these functions here. So just copy the code and then for the other function as well we do the same, copy over the code, just press enter, and now both our functions are loaded. We also have to load the foreign package. So we'll do that first. Okay, and now we'll call our function plot dm graphs. So as you can see, it throws out all the text that I have included as part of the function, which tells me that these graphs are being plotted, but I only see the final, the last graph that this function plots in this section. If I want to see all the graphs, or the previous graphs that this function has generated, then I need to click on this back button here, and so this will show me the previous plot. And so when I go back, this shows me the correlation between diabetes and physical inactivity, between obesity and physical inactivity, then between diabetes and obesity, and I can keep navigating back and forth between the graphs as I want using these two buttons. So again, these show a positive correlation between diabetes and obesity, a positive correlation between obesity and physical inactivity, and then a positive correlation between diabetes and physical inactivity. And this shows that the trend between 2004 and 2012, and this blue line is for obesity, or the percentage population that is obese, and the red line is for the percentage of population that's diabetic, and this green line is for the percentage of population that's inactive, physically inactive during their leisure time. And it shows how these are rising trends across the US, and this gives us critical insights out on how to delay the onset of diabetes, and in some cases perhaps even be able to completely avoid getting diabetes. Now we run the second function, which is the plot BMI graphs. So I'm going to call this function here. As you can see, this function has also plotted all the three graphs. This is the final graph that this function plots along with the regression model line here, which shows a negative correlation between green vegetables consumption per day and BMI, which is an indicator of obesity, which tells us that our increased consumption of green vegetables is good for keeping our weight down, is good for keeping our BMI and hence obesity down, and furthermore can then help us prevent or delay the onset of diabetes. Of course, in addition to many other factors that may be in play here, but this specifically just addresses some of these foods that we eat and how they can play a part in keeping us healthier and avoiding getting some of these diseases. Again, if you want to see the previous graphs, we go to the back button here. This should show us the previous graphs that are plotted. Again, this will take a little bit of extra time. This shows us the correlation between vegetable consumption and BMI. The relation is not as clear as we saw earlier for the green vegetables versus BMI, but from this line here we can see that this is also somewhat negatively correlated. And then we see the first graph that was plotted by this function. This is our correlation between total fruits and vegetables consumption per day and BMI. Again, the negative correlation here is not as clear. You can somewhat make it out from this line, but the regression model line is somewhat straight. I looked at the total fruits and vegetables first. It did not give me a satisfactory answer, and so I looked at the just the vegetables consumption and BMI next. And again, it wasn't really what I was looking for in terms of showing a very clear relationship. And then I looked at the consumption of only green vegetables and BMI, and that showed me a much more clearer picture of negative correlation, and that's where I stopped. Of course, we can further enhance and improve this model, perhaps look at polynomial regression models, etc. And some of those might give us a better fitting model, but I wanted to sort of contain the scope of this exercise to studying these few variables and only through linear regression models, and so this is what we have right now. Thank you so much for watching.